Two multiple pipe systems, two or more pipes. If you can solve the equation for one pipe system, you can solve them all. But when system contains two or more pipes, certain basic rules make the calculation very smooth. Any resemblance between these rules and the rules for handling electric circuit is not coincidental. In this figure, there are three types of pipe system. The first part is pipe in series. The first is the set of three pipes in series. Rule 1 is that the flow rate is same in all pipes. So the first rule is the flow rate is same on all pipes. Is same in all pipes. Q1 equals to Q2 equals to Q3. So we can write V1 D1 square, V2 D2 square, and D3 D3 square. This is the relation for the same flow rate in all pipes, and the rule 2 in this type of pipe system is that the total head loss through the system equals the sum of the head loss of each pipe. Total head loss is equals to the summation of all head loss. Delta H1, delta H2 plus delta H3, where delta H is a quantity. We have a relation for delta H as a function of friction factor V2 on 2H on D1 K as a FL on D. This is the head loss for a pipe, a function of flow properties and geometrical properties. For that can be replaced for any pipe which values geometry and also friction factor. V2 and V3 are proportional to V1 from the previous equation we said here, right here. So we can delta H on delta V or delta H head loss from A to B for a pipe in series as a function of intensity only when the for example alpha 3F3, where the alpha are dimensionalized constant. If the flow rate is given, we can evaluate the right hand side and hence the total head loss. If the head loss is given, a little iteration is needed since F1, F2 and F3 are dependent on V1 through the Reynolds number, beginning by calculating F1 and F2 and F3, assuming fully roof flow, and the solution for V1 will converge with one or more two iterations. So if we have Q flow rate, if we have flow rate, we can evaluate the right hand side of the previous equation, which was delta H. Delta H will be calculated. Excuse me. Right hand side of delta H is this expression. With Q, we can calculate velocity as V2 on 2J, friction factor as a function of Reynolds and the pipe geometrical design, and geometrical specification, and the factor for kinetic energies. But if we had head loose, we should iterate the problem with F1 and F2, F3 or other friction factor with some iteration at first at fully roof, and make some assumption for velocity and iterate the problem and obtain it F1 and F2, and iterate this process to obtain the result. The second pipe is the pipe in parallel. The second multiple pipe system is the parallel flow case, which is shown in this picture. The B part, the pipe are in parallel. Here the pressure drop is the same in each pipe, and the total pressure drop is same. Each pipe, and the total flow is the sum of the individual flows. So we can write the head loose and Q equals to Q1 plus Q2 plus Q3. This is the rules for the system of parallel pipe, for example. In this case, this is the head load is also depends on the shape of the pipe in parallel. For example, this system of pipe maybe has more friction and head loose. That if the total loose is known, it is straightforward to solve for Q1 in each pipe and sum them as will be seen in previous, as we see in this relation. This is a problem of determining the summation of the flow rates when, let me write, if total head is known, it is straightforward to solve for Q. Two is a problem of determining the summation of the flow rate when head load is known requires iterations. Each pipe is related to head loads by the multi relation as this relates. So the summation of CF on FI, where CI is the GLI. Since the friction factor vary with Reynolds number and roughness ratio for each pipe, we can calculate a first estimation of HF, then each pipe yields a flow rate estimate. So we can at first we guess HF we can calculate QI equals to CIHF on FI. And hence a new Reynolds number and a better estimate of Fi. Then repeat the equation to convert. It should be noted that both of these parallel pipe cases finding either sigma Q or HF easily for EAS software. There is some problem solved also related to this chapter. And the third section is 3 reservoir junction. Consider the flowed example of a 3 reservoir pipe junction in the picture. The third one, if all flow are considered positive toward the junction, then we have Q1 plus Q2 plus Q3 equals to 0, which obviously implies that one or two of the flows must be away from the junction. The pressure must change through each pipe so as to give the same static pressure Pj at the junction. In other words, let the hydraulic grade level at the junction have the elevation of on rho G. Where Pj is the gauge pair for simplicity, gauge pressure, then the head loads through each, assuming that P1 equals to, as gauge pressure equals to 0. So at each reservoir surface must be such that eta H1 and also for delta H2 and for the third pipe and reservoir we have on 2J F2 L2 on D3 iterating until the flow rate balance at the junction. According to this relation, if it gets Hg too high at the summation of flow rate will be negative, and the remedy is to reduce Hj and vice versa. So too high gas for Hj, too high, and we may be obtaining the negative of Q1 and Q2 and Q3 negative. So in the next case we should decrease the Hj to make calculation. There are examples related to this type of system of fluid. This is the end of this chapter. There are also some sections related to some devices, but this is not necessary to. If you want to continue with them, you can see the reference Frank and Byte fluid mechanics.